For more than a century, humanity has been leaking its location into the universe without ever asking who might be listening. The horrifying possibility is that the oldest civilizations didn't survive by exploring the cosmos. They survived by hunting anything foolish enough to announce its existence. In this video, you'll uncover the terrifying logic behind the dark forest theory and why humanity's greatest scientific achievement may also be its greatest act of self-destruction. Get ready. Let's begin. In the summer of 1950, a small group of physicists gathered for lunch at Los Alamos National Laboratory. The mood was light. Talk had turned to flying saucers, the kind of stories filling newspapers and magazines at the time, and to the tantalizing idea that faster than light travel might someday be possible. Then, almost as an aside, Enrico Fermi, one of the most brilliant scientific minds of the 20th century, looked up from his plate and asked a question that would echo through science for the next 75 years. Where is everybody? It sounds like a throwaway comment, the kind of thing said between bites of food and forgotten by dessert. But underneath that simple sentence sits one of the most disturbing contradictions in all of modern astronomy. Fermi was not asking out of idle curiosity. He was doing quiet mental math, and the math did not add up. Consider the numbers for a moment. Our galaxy, the Milky Way, is estimated to be roughly 13.6 billion years old. That is an almost incomprehensible span of time. Long enough for stars to be born, live out their entire lives, and die, generation after generation, long before our own sun ever ignited. Within a timeline that long, there has been more than enough opportunity for intelligent life to emerge somewhere else, develop technology, and begin reaching outward. Here is where the paradox sharpens into something unsettling. Even a single civilization, just one, developing the ability to travel between stars at a modest 10% of the speed of light, could in theory colonize an entire galaxy the size of ours within a few million years. On the scale of cosmic time, a few million years is not a long stretch at all. It is closer to a blink, a rounding error against a backdrop of 13 billion years. If intelligent life is even moderately common, and if the physics of interstellar travel is achievable at even a fraction of light speed, our galaxy should, by now, be humming with activity. It should show fingerprints everywhere, structures built around stars, waste heat from massive engineering projects, artificial signals threaded through the background noise of space. Instead, when we point our telescopes outward, when we tune our receivers to the sky, we get nothing. Not a single confirmed signal in over 60 years of active listening. Not one artificial structure detected among the billions of stars we have studied. Not one verified piece of evidence, anywhere, that another civilization has ever existed. The silence is not partial. It is not scattered or inconsistent. It is complete. This is the heart of what scientists now call the Fermi Paradox. And it is important to understand what kind of problem this actually is. This is not simply a case of humanity not having looked hard enough yet. Our instruments have scanned millions of stars. Our search has spanned decades. This is not an evidence gap waiting to be closed with a slightly bigger telescope or a slightly more sensitive receiver. This is a mathematical contradiction. The equations say the galaxy should be full. The sky says it is empty. And for 75 years, that gap between expectation and observation has haunted some of the sharpest minds in physics, astronomy, and mathematics. Without a resolution that satisfies everyone, scientists have proposed dozens of explanations over the decades. Some argue that the leap from simple chemistry to living cells is so improbable that it may have only happened once in the entire history of the galaxy. Right here on Earth. Others argue that intelligent life is common, but something, some barrier, some filter, tends to wipe civilizations out before they ever reach the stars. And a smaller, more unsettling group of researchers has begun to ask a very different kind of question. What if life is out there? Plenty of it. And what if the silence itself is not an accident, but a choice? That last possibility is the one that keeps astronomers up at night, because it does not require life to be rare at all. It only requires civilizations to have learned something about the universe that we have not learned yet. Here is a question worth sitting with for a moment. If the universe is this old and this vast, which possibility unsettles you more? That there is truly no one else out there, or that there are many others, and they have all chosen to stay quiet on purpose, because it turns out the very same equation once used to promise us thousands of cosmic neighbors is now being used by some scientists to explain why we might never hear from a single one of them. 11 years after Fermi's question hung in the air over that lunch table, another scientist tried to give it a shape. In 1961, astronomer Frank Drake sat down ahead of a small conference at the Green Bank Observatory in West Virginia and wrote out a formula on a chalkboard. One meant to organize the guesswork into something more disciplined. It became known as the Drake equation, and it remains one of the most famous formulas in the history of science, not because it gives us a precise answer, but because of what it forces us to confront. The equation is not complicated once you strip away the notation. It simply multiplies together 7 factors, each one narrowing the funnel a little further, until what remains is an estimate of how many civilizations in our galaxy might currently be capable of sending out a detectable signal. The first factor is the rate at which new stars form in our galaxy each year. The second is the fraction of those stars that actually have planets orbiting them. The third narrows things further, asking how many planets per star could realistically support life. The fourth asks what fraction of those planets actually develop life at all. The fifth pushes deeper still, asking what fraction of that life evolves into intelligence. The sixth asks how much of that intelligent life develops technology capable of broadcasting a signal into space. And the seventh, the final piece, asks the hardest question of all. How long does such a civilization survive while it is still broadcasting? When Drake first wrote this out in 1961, almost every number in that equation was a guess dressed up as science. We had no real data on how many stars had planets, let alone how many of those planets might harbor life. It was, at the time, more of a framework for discussion than a tool for calculation. But something remarkable happened in the decades that followed. Real data began filling in those blanks, and the picture that emerged was far more generous than anyone in that Green Bank meeting room could have imagined. NASA's Kepler Space Telescope, launched in 2009, spent years staring at a single patch of sky, watching for the tiny dimming of starlight that happens when a planet passes in front of its star. What it found reshaped our entire understanding of the galaxy. Planets, it turns out, are not rare exceptions scattered here and there. Nearly every star we study seems to host at least one, and a meaningful share of those planets sit inside what astronomers call the habitable zone, the narrow band of distance from a star, where temperatures allow liquid water to exist on a planet's surface. The single condition scientists consider most essential for life as we understand it. That number, the fraction of planets sitting in a habitable zone, has turned out to be significantly higher than the cautious estimates researchers were working with back in 1961. Star formation rates are well measured now. Planet frequency is well measured now. Even the conditions for habitability are far better understood than they were 2 generations ago. In other words, 6 of the 7 variables in Drake's equation have only grown more hopeful with time, not less. The raw ingredients for life appear to be scattered generously across our galaxy, far more generously than early scientists dared to assume. And that is exactly what makes the 7th variable so unsettling. That final factor, the length of time a civilization survives once it becomes capable of reaching out to the stars, the one scientists label simply as SL, remains almost completely unknown. It is the one number in the entire equation that no telescope, no data set, no observation has been able to pin down. Think about what that really means. We now have strong evidence that the galaxy is filled with planets, filled with the right conditions, filled with the raw potential for life to arise again and again, and yet the sky remains silent. If nearly every other piece of the puzzle points toward abundance, then the missing piece, the survival time of an advanced civilization, may be the single number responsible for the entire paradox. It may be the difference between a galaxy that should be crowded with neighbors and the empty, quiet one we actually observe. Some scientists believe that number could be enormous. Civilizations lasting for tens of thousands or even millions of years once they master the technology to broadcast into space. Others suspect the number is disturbingly small, perhaps only a few centuries. A narrow window that opens the moment a species learns to send radio waves into the sky, and closes not long after, for reasons we have not yet had to face ourselves. If you had to place a bet, how long do you think an average technological civilization survives before it goes silent? 100 years? 1,000 years? Or perhaps a million? Because right now, we are the only data point science actually has, a living experiment still running, and without realizing it, we have already done something that can never be taken back. By the time Frank Drake stood at that chalkboard in Greenbank, humanity had already done something it did not fully understand the weight of. 6 decades earlier, in 1901, an Italian inventor named Guglielmo Marconi accomplished something newspapers across 2 continents called nothing short of a miracle. Standing on the coast of Newfoundland, he received a radio signal sent from a transmitter across the Atlantic Ocean in Cornwall, England, proving for the first time that a message could cross an entire ocean without a single wire connecting sender to receiver. Many scientists of the era had doubted it was even possible, insisting the curve of the Earth itself would block any such signal from traveling that far. Marconi proved them wrong in an instant. At the time, the achievement was celebrated purely as a triumph of engineering, a new way for ships to talk to shore, for nations to talk to one another. Nobody standing on those cliffs understood they had just opened a door that could never again be closed. Because a radio wave, once it leaves its source, does not simply arrive at its intended destination and stop there. It keeps going. It travels outward in every direction it was aimed, at the full speed of light, indifferent to oceans, indifferent to continents, indifferent to the edge of our own atmosphere. Marconi's transatlantic signal did not settle quietly over the ocean. It kept climbing, past the clouds, past the moon, out of our solar system entirely, and it has not slowed down since. Every transmission that followed did the very same thing. Every early radio broadcast, crackling out of living rooms in the 1920s, every wartime communication sent during the Second World War, coordinating ships and warning of incoming raids. Every radar sweep built during the Cold War to scan the horizon for danger, every television signal that carried the first moon landing into millions of homes, every satellite transmission bouncing data across the globe, all of it left Earth. All of it is still leaving Earth, at this very moment, without pause. Physicists have calculated roughly how far that expanding wavefront now reaches. The leading edge of humanity's accidental broadcast now stretches more than 100 light-years outward from Earth in every direction, quietly enveloping thousands of stars along the way, and it grows wider by exactly 1 more light-year with every single year that passes. It does not slow down. It does not fade into nothing. It simply keeps expanding, silently, into deeper reaches of the galaxy that we ourselves have never seen. What makes this fact especially unsettling is not the distance itself, but the permanence of it. There is no mechanism, no technology conceivable within the laws of physics as we understand them, that could reach out into space and call any of those signals back. Once a wave of radio energy leaves an antenna and crosses beyond our atmosphere, it belongs to the universe, not to us. We cannot edit it. We cannot apologize for it. We cannot decide, after the fact, that we would rather not have said what it said. It simply continues, forever, carrying an honest record of exactly who we were the moment it left our world. There is, however, a curious twist buried inside this story, one that seems almost too fitting to be coincidence. In the decades since television towers and high-powered military radar dominated our communication, human technology has quietly begun to change its habits. Much of our communication today no longer leaks wastefully into the sky. It runs instead through fiber optic cables buried beneath the ground, or through tightly focused satellite beams aimed with precision at a single receiving dish, rather than broadcast openly in every direction at once, without any coordinated decision, without any single policy or treaty ever being signed. Humanity's electromagnetic noise, the loud, careless kind that once spilled freely into space, has been quietly shrinking for years. If a civilization somewhere out there has spent decades listening for exactly this kind of accidental noise, then Earth may have already passed through its loudest, most exposed chapter without ever realizing it, and started learning, almost by accident, how to lower its voice before it was too late. Did you know that right now, the voices of World War II radio broadcasters are still traveling among the stars? If that is true, then the question is no longer whether extraterrestrial life exists, but how long they have already known about us. For decades, scientists searched for a scientific answer to why the galaxy sounded so empty. It took a novelist, not a physicist, to give that silence its most chilling explanation. In 2008, Chinese science fiction author Liu Cixin published a book called The Dark Forest, the second installment in his celebrated trilogy that began with the three-body problem. The English translation arrived in 2015, and with it came a concept that quietly slipped out of fiction and into serious scientific conversation, discussed at conferences, debated by astrophysicists, and eventually referenced even by policy circles concerned with how humanity should conduct itself in space. The idea itself is built on something far older than the novel that popularized it. It rests on game theory, the branch of mathematics that studies how rational players behave when their outcomes depend on decisions made by others they cannot fully predict. Liu Cixin took that framework and scaled it up to the size of the universe, and what emerged was a version of the cosmos that looks nothing like the hopeful, communicative galaxy imagined by earlier generations of scientists. The theory rests on two foundational assumptions, and neither one requires malice or cruelty or any dramatic villain lurking in the shadows. The first assumption is simple. Survival is the most basic driving need of any civilization, anywhere, under any circumstances. No matter how advanced a species becomes, no matter how peaceful its values, its first and most fundamental priority will always be to continue existing. The second assumption is just as simple and far more unsettling once you sit with it. No civilization can ever be fully certain of another civilization's true intentions, not through a single message, not through decades of careful observation, not even through direct contact. Intentions can shift, circumstances can change. What looks peaceful today may not remain peaceful tomorrow, and there is no reliable way, across the vast distances of interstellar space, to verify with confidence which version of the truth you are dealing with. Place these two ideas next to each other, and a cold mathematical conclusion begins to take shape. If survival is the highest priority, and if intentions can never be verified, then trust itself becomes a liability. Reaching out to an unknown civilization means gambling everything on the hope that whoever receives your message happens to be friendly, and there is no way to test that hope before you have already revealed exactly where you are. Once contact is made, once your coordinates, your technological level, and your vulnerabilities are exposed, there is no way to undo it. According to this logic, the only truly safe choice left to any civilization is either to remain silent and unseen, or, in the most extreme interpretation of the theory, to eliminate a potential threat before it has the chance to eliminate you first. It is worth being precise here, because this is often where the theory gets misunderstood. This is not a prediction that aliens are inherently evil, or hostile, or built for conquest. It is a logical outcome of uncertainty, operating at an unforgiving scale. It mirrors a concept many people already recognize from economics and political science. The prisoner's dilemma, a classic scenario in which two parties would both benefit most by cooperating, yet each has strong rational incentive to betray the other first. Simply because neither can be certain, the other will not betray them. Scale that dilemma from two prisoners in separate interrogation rooms to two civilizations separated by hundreds or thousands of light years, with no fast way to communicate, no way to negotiate, no way to build trust over time, and the incentive to stay quiet or to strike first becomes overwhelming. This is precisely why the theory carries the name it does. Picture the galaxy as an enormous, silent forest at night. Every civilization within it is a hunter, moving carefully through the trees, armed, alert, and afraid. Nobody dares light a fire, because a fire announces exactly where you are standing to every other hunter in the forest, and there is no way to know in advance whether the nearest hunter is friend or predator. The rational strategy, under those conditions, is not curiosity. It is silence, absolute, disciplined, permanent silence. Here is a question worth pausing on for a moment. In game theory, when two sides can never fully trust each other, is staying silent the rational choice? Or is striking first the rational choice? Because if that same cold logic holds true on a cosmic scale, then one of humanity's proudest achievements, the deliberate act of sending a greeting out into the stars, may turn out to be the single most dangerous decision our species has ever made. In 1996, an economist and physicist named Robin Hanson, working at George Mason University, sat with the same haunting question that had occupied Fermi and Drake before him, and offered the scientific community a new framework for thinking about it. He called it the Great Filter, and it remains one of the most widely discussed explanations for cosmic silence to this day. The idea works like this. Somewhere between the birth of a planet and the rise of a civilization capable of reaching the stars, there exists a barrier, a step so difficult, so improbable, that almost nothing manages to pass through it. Hansen called it a filter, because that is precisely how it behaves. Countless planets may begin the journey toward intelligent, spacefaring life, and yet only a vanishingly small number ever make it out the other side. The great unresolved question, the one that gives this theory its weight, is where exactly that filter sits along the timeline of evolution. There are two possibilities, and they lead to two very different futures for humanity. The first possibility is that the filter lies somewhere behind us. Perhaps the leap from simple, lifeless chemistry to the first living cell is staggeringly rare. A combination of conditions so precise that it may have only happened once across the entire history of our galaxy. Or perhaps the harder step was the jump from single-celled organisms to complex, multicellular life, a transition that took billions of years to occur even here on Earth, and one biologists still do not fully understand. If either of these leaps represents the true filter, then humanity has already cleared the hardest hurdle in the universe without ever realizing it. Under this version of events, we are not early. We are simply rare, an improbable success story standing on the far side of a wall that stopped almost everyone else. The second possibility is far less comforting. What if the filter does not sit behind us at all, but somewhere ahead, waiting? What if the leap from simple life to intelligence, and even the leap from intelligence to technology, is not particularly difficult, and the true bottleneck is something else entirely: the ability of a technological civilization to survive its own power? Under this version of the theory, civilizations across the galaxy may rise again and again, build their radio towers, split their atoms, and reach the edge of the stars, only to destroy themselves before they ever get there. This is not idle speculation confined to universities. Scientists, including senior science advisors who have served multiple American presidential administrations, have spent decades naming the specific threats they believe could serve as exactly this kind of filter for our own species. Nuclear weapons sit at the top of that list. The same technology that first allowed humanity to look up at the stars with modern telescopes also handed us, within the very same generation, the ability to erase our own civilization within hours. Uncontrolled climate change stands beside it. The slow, compounding damage of a species reshaping its own atmosphere faster than it can adapt to the consequences. And more recently, a newer concern has entered the conversation: artificial intelligence advancing at a pace few governments or institutions feel prepared to manage. A technology capable of accelerating discovery, but also, some researchers warn, of slipping beyond meaningful human control. There is a real, physical symbol that captures this anxiety, one many older Americans have watched evolve across their own lifetimes. Since 1947, the Bulletin of the Atomic Scientists has maintained what is known as the Doomsday Clock, a symbolic countdown to global catastrophe, adjusted each year based on the world's most pressing existential threats. In January of 2025, the Bulletin moved that clock to 89 seconds before midnight, the closest it has ever stood to catastrophe in its 78-year history. For a generation that remembers backyard bomb shelters, civil defense drills, and the ever-present tension of the Cold War, that number is not an abstraction. It is a continuation of a fear many of them have carried since childhood, now measured in seconds instead of minutes. If the Great Filter is real, and if it does sit somewhere ahead of us rather than behind, then these are not separate, unrelated headlines competing for attention on the evening news. They may be candidates for the very same test that has already ended countless other civilizations across the galaxy before they ever had the chance to build a telescope powerful enough to look back. If you had to guess, which filter do you think poses the greatest danger to humanity's future? Nuclear war, climate collapse, or artificial intelligence slipping beyond our control? And if a filter like this truly exists, then the silence of the universe is not a mystery at all. It is an enormous gravestone, marking the final resting place of millions of civilizations that never managed to pass the same exam. By the 1970s, the silence coming from the stars had already produced more questions than answers, and scientists kept searching for new ways to explain it. In 1973, an astronomer named John A. Ball, working at the Massachusetts Institute of Technology, proposed an idea that sounded almost too strange to take seriously at first, and yet it has remained part of serious scientific conversation for over 5 decades. He called it the zoo hypothesis, and its central claim is unsettling precisely because it does not require anyone to be hostile at all. The idea begins with a simple shift in perspective. What if the galaxy is not empty? What if it is not even hiding out of fear, the way the dark forest theory suggests? What if, instead, advanced civilizations exist in great numbers, scattered across the Milky Way, and they have simply agreed, through some shared code of conduct none of us have ever seen, to leave young civilizations alone, not because they are afraid of us, not because they see us as a threat, but because they consider us unready. The same way a biologist studying a fragile ecosystem chooses to observe from a distance rather than step into the habitat and disturb it. Think about how humans already behave toward the natural world when we believe intervention would cause more harm than good. Wildlife researchers studying an isolated tribe or a newly discovered species deep in a rainforest often follow strict rules against direct contact. They watch, they record, they resist the urge to introduce themselves because they understand that even a well-meaning introduction can permanently alter or destroy the thing they are trying to study. Some conservationists maintain enormous protected reserves specifically designed to keep human influence out entirely, allowing an ecosystem to develop exactly as it would have without outside interference. The zoo hypothesis simply scales the same instinct up to a galactic level. Earth, under this theory, is not an accident lost in a random corner of space. It is a protected exhibit, quietly monitored by observers who have chosen restraint as their guiding principle. There is something almost eerie about how well this idea maps onto our current situation. Every signal we have sent since Marconi first crossed the Atlantic in 1901 has gone unanswered. Every deliberate greeting, every scientific milestone, every nuclear test, every moon landing has apparently vanished into silence, according to this theory, not because nobody noticed, but because whoever did notice has followed a rule stricter than curiosity. Perhaps there is an unspoken threshold civilizations are expected to cross before contact becomes acceptable. Perhaps it involves surviving certain dangers on our own. Perhaps it involves demonstrating some form of collective wisdom we have not yet achieved. Under the zoo hypothesis, humanity is not ignored. Humanity is waiting for a door that has not yet been unlocked. What makes this theory particularly interesting is how it interacts with the dark forest theory discussed earlier. On the surface, the two explanations sound completely different. One imagines a galaxy full of hunters, terrified of being seen. The other imagines a galaxy full of quiet custodians, deliberately choosing not to interfere. Yet both theories arrive at the exact same observable outcome: total silence, a sky that reveals nothing no matter how carefully we listen. This is one of the more humbling realities of studying the Fermi Paradox. Multiple explanations, built on completely different assumptions about the nature of other civilizations, can produce identical results here on Earth. The silence itself does not tell us which explanation is correct. It only tells us that whatever is happening out there, it consistently ends in quiet. It is worth pausing here to be fair to the scientific process, because not every idea discussed on this channel carries equal scientific weight, and honesty about that difference matters. Compared to the Great Filter, which rests on measurable evolutionary and technological bottlenecks, we can study directly through our own history. The zoo hypothesis is far harder to test. Researchers at institutions like the SETI Institute have pointed out that there is currently no reliable way to distinguish between a universe where advanced civilizations are deliberately avoiding contact and a universe where no one capable of contact exists at all. Both scenarios look identical from behind a radio telescope. That does not make the zoo hypothesis worthless as an idea. It simply means it belongs, for now, closer to philosophy than to hard astrophysics, a possibility worth holding loosely rather than a conclusion worth defending firmly. If we truly are being watched, but judged not yet mature enough for contact, what do you think that milestone would actually be? Surviving our own weapons, solving problems as one united species rather than competing nations, learning to explore space without repeating the mistakes of our own history. But there is one recorded event, fully documented in official scientific archives, that once convinced an entire team of astronomers, even if only for a single evening, that perhaps that threshold had finally been reached. It lasted just 72 seconds. On the evening of August 15th, 1977, a radio telescope known as Big Ear, operated by Ohio State University, was quietly doing what it had done for years, scanning the sky in a slow, methodical search for anything unusual. Big Ear was not a glamorous instrument. It looked more like a flattened field of metal than the sleek dish most people imagine when they picture a telescope aimed at the stars. But that night, buried inside the printed data it had collected, it caught something that no one working on the project had ever seen before, and nothing quite like it has been seen since. The signal arrived at a frequency close to 1420 megahertz, a number that means very little to most people until you understand why astronomers consider it significant. That frequency corresponds almost exactly to the natural emission line of neutral hydrogen, the most abundant element in the entire universe. For decades, scientists searching for extraterrestrial intelligence had theorized that if any civilization wanted to be found, this particular frequency would make the most logical channel to use, a kind of universal, naturally occurring meeting point that any species with a basic understanding of physics would eventually discover on their own. It was, in a sense, the one frequency scientists expected a truly intentional greeting to arrive on. The signal itself was strong, far stronger than the background noise Big Ear normally recorded. It lasted for 72 seconds, matching almost precisely the amount of time the telescope's fixed field of view would have taken to sweep across a single point in the sky as the Earth rotated beneath it. Exactly the kind of behavior you would expect from a real, distant external source rather than a stray reflection or a piece of malfunctioning equipment nearby. A few days later, an astronomer named Jerry R. Amon was reviewing the stack of printouts from that overnight run when he reached the sequence of characters representing that unusual burst. He circled it in red ink and wrote a single word in the margin beside it. Wow. That handwritten note, almost an afterthought at the time, gave the signal the name it still carries today, the WOW signal, one of the most famous unresolved mysteries in the history of American astronomy. Here is where honesty about the evidence matters more than excitement about the story. Despite extensive follow-up searches, using the same telescope, and later using far more sensitive instruments, that exact signal has never repeated. Not once, not in the same location, at the same frequency, under any conditions scientists have been able to reproduce. To this day, decades later, there is no explanation for the WOW signal that has earned full acceptance from the broader scientific community. In 2017, one researcher proposed that the signal might have come from a pair of comets passing through the region at the time, releasing hydrogen gas that could theoretically produce a similar reading. That explanation received significant media attention, but it also drew serious criticism from other astronomers, who pointed out inconsistencies that the comet theory failed to fully resolve. No consensus was ever reached. The mystery technically still remains open. This is precisely why the WOW signal deserves to be treated with more care than casual internet legend. It is not a rumor. It is not an exaggerated story passed down through unreliable retellings. It is a documented event, recorded on real equipment, reviewed by trained professionals, and preserved in the official archives of Ohio State University. Whatever caused it, something arrived at Big Ear that night that still cannot be fully explained using known natural sources. If you were the scientist standing there, reviewing a printout showing a signal exactly like the one theory predicted an alien civilization might send, arriving once and then vanishing forever without any trace or repetition, what would you allow yourself to believe? But here is the detail that makes this story far more unsettling than the mystery itself. 3 years after that signal was recorded, in 1974, it was not aliens who sent a message out into the silence of space. It was us. And unlike the WOW signal, our transmission did not vanish anonymously into the dark. It carried, deliberately encoded within it, the exact coordinates of home. On November 16, 1974, at the Arecibo Observatory, nestled among the limestone hills of Puerto Rico, a team of scientists gathered around one of the most powerful radio transmitters on the planet and did something no one on Earth had ever attempted with quite this level of deliberate intention. They pointed the massive dish, a structure so large it had been built directly into a natural sinkhole in the landscape, toward a distant cluster of stars, and they sent a message outward into the dark. The transmission lasted just 3 minutes. Its destination was a globular cluster known as M13, a tightly packed swarm of several 100,000 stars sitting roughly 25,000 light-years from Earth. The message itself was not a greeting in the way most people imagine when they picture first contact. There were no words, no spoken language, nothing that assumed the recipient would share anything resembling human culture. Instead, the team encoded everything into a simple stream of binary digits, ones and zeros, chosen specifically because mathematics is considered the one language that any sufficiently advanced civilization, anywhere in the universe, would almost certainly understand. Arranged correctly, those binary digits formed a picture a kind of cosmic postcard describing exactly who we are. It included the basic counting numbers from 1 to 10. It included the atomic numbers of the elements that make up DNA. It included a simplified diagram of the double helix structure itself, along with an estimate of the human population at the time. It included a rough sketch of a human figure, along with the average height of a person, expressed in units tied to the wavelength of the transmission. It included a simple diagram of our solar system, highlighting the third planet from the Sun as our home. And finally, it included a small illustration of the Arecibo telescope itself, the very instrument that had sent the message, along with its diameter. As if signing the letter with a return address, the message was assembled by a team led by the astronomer Frank Drake, the very same scientist who had written the famous equation discussed earlier in this story, working closely with Carl Sagan, one of the most recognizable scientific voices of the 20th century. Along with several colleagues at Cornell University, together, they had built what many people came to describe as humanity's first cosmic business card, a compact, careful introduction meant to represent our entire species in a single burst of structured light. Here is the detail that turns this achievement into something closer to a meditation on mortality than a simple scientific milestone. Traveling at the speed of light, the fastest anything can move according to the laws of physics as we understand them. That message will not arrive at its destination until roughly the year 27,000, not 2,700, 27,000. Nobody alive today will ever know whether it was received. Nobody's grandchildren will know. Nobody's grandchildren's grandchildren, repeated across hundreds of future generations, will live to see the answer, if an answer ever comes at all. It is, in the most literal sense possible, a message written for a version of humanity so far removed from us that we cannot even meaningfully imagine what that future civilization, should it still exist by then, might look like, or whether it would still recognize its own reflection in an image sent by ancestors so distant in time. There is a particularly painful postscript to this story that many people, especially those who remember watching this dish appear on television screens throughout their lives, will already feel in a personal way. The Arecibo Observatory was not just a research facility, it was a cultural icon, appearing in the 1997 film Contact, based on Carl Sagan's own novel, and famously serving as the dramatic backdrop for a pivotal scene in the 1995 James Bond film GoldenEye. For over half a century, that enormous dish, suspended above the Puerto Rican jungle by a network of massive support cables, stood as one of the most recognizable symbols of humanity's search for company among the stars. In December of 2020, following years of structural strain and a series of cable failures that engineers had struggled to repair, the platform suspended above the dish collapsed entirely, destroying the telescope beyond any hope of restoration. For the scientific community, and for a generation of Americans who had grown up watching that dish stand quietly against the sky, it felt like losing something closer to a monument than a piece of equipment. If the decision had been placed entirely in your hands that day, in 1974, knowing that once the signal left the dish, there would be absolutely no way to call it back, no way to reconsider, no way to edit a single line of that cosmic postcard, would you have given the order to send it? But Arecibo was never the only mark humanity has left drifting through the darkness of space. It was simply the loudest, most deliberate one, somewhere else, quietly, without the fanfare of a single dramatic broadcast. A far larger and far more patient search has been unfolding, one designed not to speak outward into the silence, but to listen for whatever might be speaking back. In 2015, a Russian-born investor named Yuri Milner stood beside the physicist Stephen Hawking to announce something unlike anything the search for extraterrestrial intelligence had ever seen before. It was called Breakthrough Listen, and it arrived with a level of funding that instantly dwarfed almost every previous effort in the field. $100 million, committed over a period of 10 years, dedicated entirely to one goal: scanning the sky more thoroughly, more precisely, and more continuously than humanity had ever attempted before. It remains, to this day, the largest scientific search for extraterrestrial intelligence in recorded history. The program did not rely on a single instrument. It combined the power of some of the most capable radio telescopes on Earth, including the Green Bank Telescope in West Virginia, the very same observatory where Frank Drake had first written his famous equation decades earlier, along with the Parkes Telescope in Australia, a facility with its own long and storied history in radio astronomy. Together, these instruments have been used to scan millions of the nearest stars to our own solar system, along with a focused, sustained study of the crowded, star-dense center of our own galaxy, the place many scientists consider the most statistically promising region to search for any sign of intelligent activity. Modern searches like this one operate along two parallel tracks, each looking for a different kind of clue. The first is what scientists call a technosignature, any detectable sign of technology itself. Something like an artificial radio transmission, an unusual pattern of light that could indicate massive engineering on the scale of an entire star system, or any signal so precisely structured that natural astrophysical processes struggle to explain it. The second is what scientists call a biosignature, evidence not necessarily of intelligence, but simply of life itself, chemical fingerprints in a planet's atmosphere that suggest biological activity is occurring somewhere on its surface, even if that life never develops anything resembling technology or civilization at all. This is exactly where one of the most powerful instruments ever built has entered the picture. The James Webb Space Telescope, launched in 2021, has been steadily turning its extraordinary sensitivity toward the atmospheres of distant exoplanets, breaking down their light into its component wavelengths to search for chemical signatures that might hint at biological processes. Scientists are particularly interested in unusual combinations, such as the simultaneous presence of oxygen and methane in a planet's atmosphere, a pairing that on Earth exists almost entirely because living organisms continuously replenish both gases. Finding that same chemical imbalance somewhere else would not prove the existence of alien life on its own, but it would represent one of the strongest indirect clues science has ever gathered. And these findings, when they emerge, are published through peer-reviewed research conducted in partnership with both NASA and the European Space Agency. It is important, in the spirit of scientific honesty that has guided this entire story, to be completely clear about where things currently stand. As of today, not a single discovery from any instrument in any peer-reviewed study has been confirmed by the broader scientific community as definitive evidence of life beyond Earth. There have been intriguing signals. There have been unusual chemical readings that sparked excitement and debate, but nothing has crossed the threshold required to be called proof. This distinction matters because it would be easy and dishonest to blur the line between a promising clue and a confirmed answer. If you consider the pace of discovery over just the last decade, the improvements in telescope sensitivity, the sheer scale of funding now dedicated to this search, do you think there is a realistic chance you might live to witness a genuinely historic announcement in your own lifetime? But while these vast, patient, well-funded searches continue quietly scanning the depths of space, something far smaller, far stranger, and far less expected once passed directly through our own solar system, close enough to study in detail. And it left a team of serious researchers at Harvard asking a question that no one had seriously entertained before. Had a visitor from another star already come and gone, without us ever fully understanding what we were looking at? On October 19, 2017, a telescope in Hawaii called Pawn Stars, designed specifically to scan the sky night after night for anything moving in an unexpected way, caught sight of an object unlike anything astronomers had ever confirmed before. It was moving too fast to belong to our solar system. Its trajectory, when traced backward and forward through the calculations, revealed something remarkable. This object had not originated anywhere near our sun. It had come from somewhere else entirely, drifted across the vast emptiness between the stars for who knows how long, and simply passed through our solar system on its way back out into the darkness. Astronomers gave it a name drawn from the Hawaiian language, Mu'a, meaning roughly a messenger from afar arriving first. A name chosen because this was, officially, the very first interstellar object ever confirmed to have visited our solar system. Almost immediately, the object began behaving in ways that did not fit comfortably into any of the categories astronomers were used to. Most objects passing through our solar system, comets and asteroids alike, tend to be roughly round, or at least broadly proportioned in a way that suggests a natural gravity-shaped clump of rock or ice. Oumuamua was different. Based on the way sunlight reflecting off its surface changed dramatically as it tumbled through space. Researchers calculated that it had to be extraordinarily elongated, some estimates suggesting a shape many times longer than it was wide, closer to a cigar or a flattened plate than anything resembling a typical asteroid. Its brightness flickered as it rotated, swinging wildly in ways that reinforced just how strange its proportions appeared to be. Then came the detail that pushed this story from unusual into genuinely puzzling. As Oumuamua left our solar system, astronomers tracking its path noticed a small, measurable acceleration, a slight extra push in its trajectory that could not be fully explained by the sun's gravity alone. Comets sometimes experience something similar when ice on their surface heats up and releases gas, creating a faint jet that nudges their path slightly off course, something scientists call outgassing. The problem was, when researchers looked for the telltale signs of outgassing around Oumuamua, the visible tail, the surrounding cloud of dust and gas that comets typically produce, they found essentially nothing. The acceleration was real. The expected explanation for that acceleration was missing. Here is where scientific honesty requires presenting both sides of this story fully and fairly. The majority of professional astronomers, including a large research team whose findings were published in the prestigious journal Nature, concluded that Oumuamua was most likely a natural object, perhaps a fragment of a shattered planet from another solar system, or an unusually shaped chunk of ice and rock that behaved strangely under conditions we simply do not fully understand yet. Given that we had never observed an interstellar object up close before this one, under this view, the mystery is not evidence of anything artificial. It is evidence that the universe still has physical processes capable of surprising us, and that a single, brief observation, without the ability to send a probe to examine it directly, leaves plenty of room for uncertainty. At the same time, this was not a fringe controversy invented by amateur speculation. Avi Loeb, a respected astrophysicist and former chair of the astronomy department at Harvard University, publicly argued that the object's unusual shape, its strange acceleration, and the complete absence of a visible cometary tail together made a natural explanation genuinely difficult to fully justify. And he suggested that the possibility of an artificial origin, perhaps some form of discarded technology or probe from another civilization, deserved serious scientific consideration rather than dismissal. His position triggered substantial debate within the astronomical community, with many colleagues pushing back firmly, while others acknowledged that Oumuamua remained, at minimum, one of the strangest objects modern astronomy has ever documented. The object is gone now, moving further away from us with every passing day, well beyond the reach of any instrument we currently possess. We will likely never get another close look at it. Whatever it truly was, the debate surrounding it remains unresolved, sitting exactly where honest science should leave a question that cannot yet be answered with certainty. If another object exactly like this one appeared again someday, moving through our solar system without pausing, without responding to any signal we sent toward it, and continued on its way exactly as Oumuamua did, would you consider that pure coincidence, or something closer to quiet, deliberate observation? Whatever Oumuamua ultimately was, it left behind a genuinely unsettling reminder. If a civilization somewhere possesses technology advanced enough to explore other star systems without announcing itself, there may be no reliable way for us to ever know, with any confidence, when exactly we are the ones being studied. Long before questions of intention or hostility even enter the conversation, there is a much simpler, far more fundamental barrier standing between humanity and any other civilization that might exist among the stars. It has nothing to do with fear, or game theory, or hidden agendas. It has to do with the basic architecture of the universe itself, and the one rule that Albert Einstein's theory of relativity established as absolute: nothing. No signal, no spacecraft, no form of information of any kind can travel faster than the speed of light. This limit is not a matter of current engineering falling short of some achievable future breakthrough. It is a fundamental property of space and time themselves, confirmed repeatedly through more than a century of rigorous experimentation and observation. Light speed represents the fastest that cause can ever produce effect anywhere in the universe. And once you accept that limit as absolute, the true scale of cosmic distance stops being an abstract number and starts becoming something closer to a wall. Consider the nearest star system to our own, Proxima Centauri, sitting roughly 4.24 light-years away. That distance sounds almost approachable when compared to the vastness of the rest of the galaxy. And yet, even at the absolute maximum speed the universe allows, a radio signal sent from Earth toward that star would take more than 4 years just to arrive. If anything there responded immediately upon reception, with zero delay of their own, that reply would then take another 4 years to travel back to us. A single exchange, one message sent and one message received in return, would require more than 8 years from start to finish, and that is for the closest star system in existence, one that, as far as we currently know, does not even host a habitable planet capable of supporting complex life. Now extend that same math outward to distances far more representative of where habitable, potentially inhabited star systems are estimated to sit within our galaxy. Distances measured not in single-digit light-years, but in the hundreds, or even thousands. A single round-trip conversation under those conditions would not take years. It would take centuries. An entire human lifetime would not be long enough to witness one complete exchange from beginning to end. Entire civilizations could rise, transform, and collapse before a single follow-up question ever received its answer. Under these conditions, the word diplomacy, as humans understand and practice it, effectively stops meaning anything at all. There is no room for clarification, no room for back-and-forth negotiation, no opportunity to correct a misunderstanding before it hardens into permanent consequence. This matters enormously once you consider how fragile trust already is, even under the best possible conditions available to us here on Earth. Throughout human history, nations sharing the same planet, the same rough timescales, and often even overlapping cultures and languages have still repeatedly fallen into conflict, driven by miscommunication, delayed information, and simple failure to understand one another's true intentions in time to prevent disaster. Diplomatic crises during the 20th century alone have shown how dangerously close entire nations can come to catastrophe simply because a message arrived too late or was interpreted incorrectly under pressure. If misunderstanding remains a persistent danger, even when two parties can exchange information within minutes or hours, then stretching that same fragile process across years, decades, or centuries does not simply increase the risk of miscommunication. It multiplies that risk far beyond anything humanity has ever had to manage before. If a single conversation required an entire century to produce just one reply, would you honestly still consider that communication in any meaningful sense of the word? Or would it become something closer to two isolated messages passing each other in the dark, disconnected from any real, living exchange of understanding? And if genuine diplomacy truly becomes impossible once distance grows large enough, then humanity does not need to look toward the stars to understand what tends to happen next. Our own history right here on Earth, has already shown us, in painful and repeated detail, exactly what unfolds when civilizations of vastly different power and understanding finally come face to face with one another for the very first time. Before humanity ever points a telescope toward another star system hoping for contact, there is a much closer place to search for an answer about what that contact might actually look like. That place is not the sky. It is our own history, written across centuries of human civilization, in records, letters, and artifacts we do not have to speculate about at all. Throughout the era of exploration and expansion that stretched roughly from the 15th through the 19th centuries, one pattern repeated itself again and again on nearly every continent where societies with significantly different levels of technology came into sustained contact for the first time. In case after case, the civilization possessing more advanced tools, weapons, and systems of organization gained overwhelming advantage over the civilization that did not, and that advantage rarely stayed balanced for long. Sometimes the outcome was driven by deliberate conquest. Just as often, it was driven by something far less intentional and, in some ways, far more unsettling. Diseases carried unknowingly by explorers and settlers swept through populations that had never been exposed to them before, causing losses on a scale that dwarfed anything achieved through direct conflict. Historians studying the Americas, for example, have documented that in many regions, the introduction of unfamiliar illnesses devastated indigenous populations long before any organized military campaign ever took place. Entire communities were transformed, and in some cases erased, not primarily through malice, but through the simple, brutal consequence of two worlds meeting without either side fully understanding what that meeting would set in motion. Cultural collision compounded the damage further. Differences in language, belief systems, and social structure made mutual understanding difficult, even when both sides approached one another with some degree of genuine curiosity rather than open hostility. Miscommunication led to broken agreements. Broken agreements led to distrust. Distrust led to conflict. And in nearly every documented instance where the technological gap between two civilizations was significant enough, that conflict resolved itself overwhelmingly in favor of the side holding the advantage, regardless of which side had actually started with peaceful intentions. It is worth being precise and careful here, because the lesson history offers is not that contact between civilizations is inherently evil, or that either side in these encounters was uniquely villainous by nature. The lesson is something colder and more mechanical than that. Power imbalance, on its own, tends to produce domination, almost as a natural consequence of the imbalance itself, independent of whether the more powerful side began the encounter with harmful intentions. Good intentions have repeatedly failed to prevent bad outcomes once one side held overwhelming advantage over the other. Explorers who documented genuine admiration and curiosity toward the societies they encountered still, in many cases, became instruments of that society's disruption or destruction, simply by the unavoidable weight of the disparity between them. This is precisely the pattern that makes serious researchers uneasy when they imagine what first contact between humanity and an extraterrestrial civilization might actually involve. If a civilization ever does reach us, having mastered interstellar travel across distances of light years, the technological gap between humanity and that civilization would almost certainly be vastly larger than any gap that has ever existed between two human societies on Earth. We are not talking about the difference between a society using metal tools and one that had not yet developed them. We are talking about the difference between a species still confined to a single planet, still burning fossil fuels, still struggling with disease and instability of its own, and a species capable of crossing the emptiness between stars. A technological distance that may be difficult to even meaningfully measure using human categories at all. If historical patterns hold any predictive value whatsoever, an encounter across that kind of gap would almost certainly not unfold as a meeting of equals, regardless of the intentions carried by whoever arrived. This raises a genuinely difficult philosophical question, one that does not have a clean, universally agreed-upon answer, even among serious researchers who study this topic closely. Does greater technological advancement tend to bring with it greater moral development, a kind of civilizational maturity that naturally softens the impulse toward domination as a species grows more capable? Or does greater technological power simply amplify whatever impulses already exist within a civilization, for better or worse, without necessarily improving its underlying character at all? There are thoughtful voices on both sides of this question, and intellectual honesty requires presenting both fairly rather than pretending the matter is settled. Optimists point to humanity's own trajectory as partial evidence in favor of the hopeful view. Compared to earlier centuries, many societies today place far greater emphasis on international cooperation, human rights, and diplomatic resolution of conflict than their ancestors did, even while retaining access to weapons of a destructive scale earlier generations never possessed. Under this view, moral growth and technological growth, while not perfectly aligned, do tend to move in the same general direction over long enough timescales, and a civilization advanced enough to cross interstellar space might, by necessity, have also solved many of the internal conflicts that plague younger civilizations like our own, since a species still consumed by war and short-term thinking may never survive long enough to develop such technology in the first place. Skeptics counter that this optimism rests on a fragile assumption, extrapolated from a single data point, our own species, over a relatively short span of recorded history. They point out that humanity still possesses nuclear weapons capable of ending civilization, still struggles with organized conflict between nations, and still allows short-term self-interest to override long-term collective well-being on issues ranging from environmental stewardship to resource distribution. Even now, deep into an age of advanced science and technology, under this more cautious view, there is no guarantee whatsoever that greater capability produces greater restraint. It may simply produce greater consequences whenever restraint eventually fails. Do you believe that a civilization advanced enough to reach us across the stars would, by necessity, also be more compassionate and restrained than we are, having presumably solved the kinds of internal conflicts that still threaten our own species today? Or do you believe that advanced technology, on its own, tells us nothing reliable about the character, intentions, or moral development of whoever wields it? If our own history is treated as any kind of reliable guide, then the most important question facing humanity is not really how to achieve successful contact with another civilization at all. The far more urgent question, the one that has quietly begun dividing serious scientists over the past several decades, is whether humanity should even be trying to make contact in the first place. And that exact question is currently at the center of one of the most consequential, ongoing disagreements in modern astronomy. Within the scientific community dedicated to the search for life beyond Earth, there exists a division that rarely makes front-page news, but carries consequences that some researchers believe could shape the entire future of our species. It centers on two closely related, yet fundamentally opposed, approaches to the same underlying question, and it comes down to a single, deceptively simple choice. Should humanity continue quietly listening to the universe, or should humanity actively announce itself and speak first? The first approach is known by an acronym many people have already encountered throughout this story. SETI, standing for the Search for Extraterrestrial Intelligence. At its core, SETI is a passive endeavor. Scientists working under this framework point telescopes and radio receivers outward, scanning the sky for any sign of a signal that might indicate the presence of another civilization, without ever transmitting anything themselves. It is, in essence, an act of careful, patient listening, gathering information without revealing anything about ourselves in return. The second approach carries a different acronym, one far less familiar to most people outside the field: METI, standing for Messaging Extraterrestrial Intelligence. Unlike SETI, METI does not simply listen, it actively composes and transmits deliberate signals outward into space, aimed at specific stars or regions of the galaxy, with the explicit goal of being noticed and, ideally, answered. The Arecibo Message discussed earlier in this story is one of the most famous historical examples of a METI style transmission, but it was far from the only one, and smaller, less publicized efforts along similar lines have continued in the decades since. The disagreement between these two camps is not simply a matter of scientific preference. It touches on questions of risk, responsibility, and who exactly has the authority to make a decision on behalf of the entire human species. On one side of this debate stand a number of highly respected scientific voices who have publicly urged extreme caution. Among the most prominent was the late physicist Stephen Hawking, who repeatedly warned, in interviews and public lectures throughout his career, that actively transmitting our location and capabilities into space could carry serious risk. Drawing direct comparisons to the well-documented history of what happened when less technologically developed societies here on Earth encountered more advanced ones for the first time, Hawking's concern was not built on certainty that danger would follow. It was built on the reasonable observation that we simply have no way of knowing what kind of intentions might be waiting on the receiving end of a signal, and that the potential downside of guessing wrong, once contact has been made and cannot be undone, could be catastrophic and completely irreversible. On the other side of this debate stand researchers and organizations, including advocacy groups such as METI International, who argue that this caution, while understandable, may already be arriving decades too late to matter. Their argument rests on a point already explored earlier in this story. Humanity has been leaking radio signals into space continuously since Marconi's first transatlantic transmission in 1901. Every television broadcast, every military radar sweep, every early radio program has already been traveling outward for well over a century, silently announcing our presence to any civilization within roughly 100 light years capable of detecting it. Under this view, any sufficiently advanced civilization capable of crossing interstellar distances to reach us would almost certainly already possess instruments sensitive enough to detect this decades-old leakage, regardless of whether we send any additional deliberate messages at all. If that is true, proponents argue, then choosing to remain deliberately silent going forward accomplishes very little in terms of actual safety, since the version of humanity already broadcast into space through pure accident may be just as detectable and just as revealing as anything we might choose to send on purpose. Both sides of this argument deserve to be taken seriously, and neither one currently holds a clear, universally accepted advantage within the scientific community. The cautious position highlights a real and sobering point, that irreversible decisions deserve extraordinary care, particularly when the potential consequences involve the safety of an entire species rather than a single research project. The more permissive position highlights an equally real point, that the horse, in some sense, may have already left the barn the moment Marconi succeeded in sending a signal across the Atlantic Ocean, long before anyone alive today was in a position to weigh in on the decision at all. Occasional symbolic transmissions have continued to be sent in the years since, often timed to commemorate significant scientific milestones or historic achievements, generally composed with careful attention from the scientific community, though for good reason. The finer technical details of how and when such messages are constructed and aimed tend to remain a matter left to specialists working within careful institutional oversight, rather than something scattered casually across public discussion. If the decision were placed entirely in your hands, and you alone had to choose on behalf of every person currently alive on Earth, would you choose to continue humanity's long-standing silence going forward, deliberately withholding any further deliberate transmissions into space? Or would you choose to continue speaking, accepting whatever risk that choice might carry, in the hope that reaching outward remains worth whatever uncertainty comes with it. The honest answer to that question may not ultimately come from astronomers, physicists, or the ongoing debate between SETI and METI at all. It may come, instead, from something far closer to home, from the way humanity chooses, in the coming decades, to face the very real, very earthly filters already standing directly in front of us, long before any answer ever arrives from the stars. Every explanation examined throughout this journey, the Fermi Paradox, the Drake equation, the Great Filter, the zoo hypothesis, and the dark forest theory itself, shares something in common that is easy to overlook once you step back far enough to see it clearly. Each one is, at its core, an attempt to imagine the psychology of a civilization we have never met, built entirely out of assumptions borrowed from the only civilization we actually understand, our own. When scientists imagine an advanced species hiding in silent terror, afraid that revealing itself might invite annihilation, they are not describing something they have observed among the stars. They are describing an instinct we recognize instantly, because we have lived it ourselves, in smaller form, throughout our own history. When researchers imagine an advanced species capable of striking first without hesitation, driven by cold calculation rather than malice, they are not reporting alien behavior confirmed through direct evidence. They are extrapolating from patterns of fear, suspicion, and preemptive defense that have shaped human conflict for as long as recorded history exists. The dark forest theory does not require us to imagine monsters. It only requires us to imagine versions of ourselves, placed under conditions of extreme uncertainty and consequence, and then scaled upward until the stakes become cosmic rather than merely national. This is worth sitting with honestly, because it reframes the entire question this story has been circling from the very beginning. The universe may indeed be silent, because civilizations out there are hiding from one another in fear. It may be silent, because advanced observers are deliberately restraining themselves out of some higher ethical principle we have not yet discovered. It may be silent simply because life, against every hopeful calculation built into the Drake equation, really is far rarer than we assumed. But notice something important buried inside every one of these explanations. None of them actually require the existence of a single alien civilization to already be true of humanity. Right here, right now, on our own planet. Consider the very real filters standing directly in front of our own species, ones that require no extraterrestrial threat whatsoever to become genuinely dangerous. Nuclear weapons remain distributed across multiple nations today, sitting in stockpiles built during a Cold War tension. Many watching this story tonight remember living through personally, capable of ending organized civilization within a matter of hours if political miscalculation or technical failure ever aligned at the wrong moment. That threat has not disappeared with the end of the Cold War. It has simply grown quieter, less discussed in daily conversation, while remaining every bit as physically real as it was during the years of backyard bomb shelters and civil defense drills. Climate change presents a slower, less dramatic version of the same underlying danger, the accumulated consequence of a technological species altering its own atmosphere and ecosystems faster than natural systems, or in some cases, political systems, can adapt to absorb the change. And more recently, the rapid acceleration of artificial intelligence has introduced a genuinely new kind of uncertainty, one that even many of the scientists and engineers building these systems have publicly admitted they do not yet fully understand the long-term implications of, particularly regarding how much control humanity will retain as these systems continue to grow more capable with each passing year. These are not science fiction scenarios borrowed from a Lou Sixon novel. These are documented, measurable, actively monitored challenges, tracked by real institutions, discussed in real policy meetings, represented by real symbols like the doomsday clock mentioned earlier in this story. a clock that has moved closer to midnight in recent years. Not because of anything happening among the stars, but because of decisions being made, or avoided, right here on Earth. If the Great Filter is real, it may not be waiting for us somewhere out among distant galaxies at all. It may already be here, embedded quietly into the everyday machinery of modern civilization, waiting patiently to see which direction humanity chooses to move. And yet, there is a genuinely hopeful thread woven through this same story, one worth giving equal weight to before closing this particular chapter of the search. Human beings have, on more than one occasion, demonstrated a real and measurable capacity to rise above exactly the kind of tribal fear that the dark forest theory assumes to be inevitable. Consider the International Space Station, a project that has continuously hosted astronauts representing the United States, Russia, and numerous partner nations in uninterrupted, cooperative operation since the year 2000, spanning a period that included serious geopolitical tension between several of those same participating countries here on Earth. Two nations capable of pointing nuclear arsenals at one another have, at the very same time, quietly continued working side by side hundreds of miles above the planet's surface, sharing oxygen, sharing research, sharing the basic responsibility of keeping one another alive in the vacuum of space. It is easy to overlook how remarkable that ongoing cooperation actually is, precisely because it has become so quietly routine that it rarely makes headline news anymore. This matters enormously for the generation watching this story unfold tonight, a generation that did not simply read about humanity's transformation from fear-driven isolation toward cautious cooperation. They lived through it directly. Many watching right now grew up during an era when massive radar installations scanned the horizon for incoming Soviet bombers, when children practiced hiding under school desks during drills meant to prepare them for a nuclear exchange that, thankfully, never came. That same generation later watched astronauts from rival nations shake hands aboard orbiting space stations, watched international science teams collaborate across borders to build telescopes capable of studying the atmospheres of planets orbiting distant stars, and watched humanity slowly, imperfectly, but genuinely begin choosing cooperation over confrontation in more arenas than anyone during the height of the Cold War might have confidently predicted. If any generation alive today understands, from lived personal experience, that civilizations are capable of evolving past their most dangerous instincts, it is this one. Perhaps that is the quiet, underlying message hidden inside the entire dark forest theory. Once you strip away its more frightening surface layer, it is not really a prophecy about what aliens will inevitably do to us. It is a mirror, held up to ask what kind of civilization we are choosing to become, entirely independent of whether anyone else out there is watching at all. A species that assumes the worst of every stranger it meets will almost certainly behave in ways that make that assumption come true. A species that manages to build trust, even slowly, even imperfectly, even under difficult and uncertain conditions, demonstrates something the universe may be quietly waiting to see confirmed. That intelligence does not have to inevitably curdle into fear. That power does not have to inevitably curdle into domination. That a civilization capable of building weapons of unimaginable destruction is also capable of choosing, deliberately, again and again, not to use them. Do you believe humanity's ultimate fate will be decided primarily by whatever is waiting for us out among the stars? Some distant civilization whose intentions we cannot yet know? Or do you believe it will be decided far closer to home, by the everyday choices we make here on Earth in how we manage our weapons, our climate, our technology, and our willingness to trust one another across the very real divisions that already exist among us? Because perhaps, after everything explored across this entire journey, the honest answer to the question that has haunted scientists since Fermi first asked it over lunch in 1950 was never actually written among the distant stars at all. Perhaps it has been sitting here on Earth the entire time, waiting quietly to be answered, not by a signal from somewhere else, but by the choices humanity makes about itself in the years still ahead. After 14 theories, 70 years of mathematics, and a century of listening, humanity has still not moved past the very edge of a map that remains, for the most part, blank. We have drawn careful lines around what we think we know and left the rest open, honest about how much still lies beyond our reach. Somewhere now, a radio dish is still turning toward the dark, still gathering data 1 second at a time, the same patient motion it has repeated for decades. The answer it is listening for may be centuries away, or it may already be closer than we understand, waiting only for us to become wise enough to recognize it when it arrives. This story will not tell you whether silence is wisdom, or whether reaching outward is worth the risk. Because the truth is, no one yet knows, and that uncertainty, more than any answer could, is what keeps science alive. It is what keeps us looking up. There are other mysteries still waiting in that same dark sky. Black holes, dark matter, signals no one has fully explained. For tonight, let this one rest. Unfinished, the way the universe seems to prefer it. Sleep well. The stars will still be there in the morning, quietly keeping their secrets a little longer.